In the early hours over hostile airspace near the Russian border, a MiG-29 pilot fixes his eyes on a ruggedized tablet wedged into the cockpit. Western targeting data streams across its screen. Moments later, French-made AASM Hammer glide bombs release, racing toward an FSB facility. These modifications let a 1980s Soviet fighter launch precision weapons at standoff ranges once thought impossible.
How did Ukraine fuse outdated avionics, NATO munitions, and civilian electronics into this hybrid strike platform? And later, how could the same principle of exploiting gaps turn low-flying swarms into one of the most disruptive weapons in the war? How can a fighter conceived in the early 1980s, years before GPS-guided weapons, deliver a precision glide bomb onto a target buried deep behind enemy lines? That puzzle is at the center of one of Ukraine's most striking wartime adaptations. The MiG-29 was built for short-range engagements and rapid interception, not for the demands of modern strike warfare. Its original avionics were analog, its navigation rudimentary, and its weapons interface shaped entirely by Warsaw Pact munitions. Yet these airframes remain a backbone of Ukraine's Air Force, now tasked with missions their designers never imagined. Integrating Western precision weapons into this platform posed immediate and obvious challenges. Systems like advanced targeting pods and standoff munitions rely on digital data buses and mission computers able to calculate weapon release points, handle GPS coordinates, and process continuous sensor updates. None of this existed in the MiG's stock configuration. Full-scale upgrade programs to add such capability would normally take years and involve deep rewiring of the airframe, time Ukraine could not spare under wartime pressure. The operational need was urgent. Russian long-range radars, command centers, and air defense nodes were directing forces across huge areas with relative impunity. Neutralizing these high-value assets meant finding a way to strike from a distance without sending pilots deep into the densest air defense zones. Western aircraft like the F-16 were still out of reach, so Ukrainian crews had to work with what was already flying. The solution was a blend of battlefield engineering and focused pragmatism. Ukrainian technicians installed a ruggedized tablet in the cockpit, running encrypted data links from ground or airborne controllers to provide real-time targeting data. In parallel, they modified the weapon pylons to pass precise coordinates into the munition while retaining the original release triggers and safety interlocks. This created a parallel digital feed that worked alongside the MiG's legacy systems, avoiding the need for an extensive rebuild while giving the pilot the critical information to deploy modern weapons. When the French AASM Hammer arrived, this work paid off. The AASM combines inertial navigation backed by GPS with an optional rocket motor, letting it strike accurately at long ranges and resist jamming. Designed for aircraft with full digital integration, it needed exact coordinates before release, something the modified MiGs could now provide through the new wiring and cockpit tablet. In practice, the pilot could confirm or key in target data. The interface would hand it to the weapon, and the hammer would glide or boost toward the aim point. This adaptation changed how the MiG-29 could fight. Instead of closing dangerously close and dropping unguided bombs, pilots could launch from well beyond the reach of many Russian surface-to-air systems. Battlefield reports described radar sites and command posts destroyed from distances that made interception far less likely. The precision reduced the number of sorties against heavily defended points, cutting risk to crews and preserving scarce aircraft. These standoff strikes had knock-on effects. Russian planners were forced to reposition valuable radars, pull certain systems back, or allocate more defenses to protect those that remained, often leaving other areas more exposed. The so-called Frankenstein fighter approach, melding Soviet airframes, hastily integrated electronics, and top-tier Western weapons, proved that even without full avionics upgrades, a legacy jet could perform suppression and strike missions in heavily contested skies. Western avionics packages, encrypted communications, and mission data links were patched in where they could be added quickly, but upgrades were focused on what could deliver an immediate operational benefit. This emphasis on rapid, functional adaptation allowed Ukraine to close capability gaps in months rather than years. The same willingness to improvise and exploit vulnerabilities was already taking shape in another domain: one where small, inexpensive platforms could sidestep the most advanced defenses, not by matching their sophistication, but by moving through the spaces those systems were never designed to see. 17 small drones skim the Black Sea at low speed, yet no radar picks them up. The advantage isn't invisibility, it's geometry. At roughly 50 meters altitude, the radar horizon is only about 25 kilometers away. Below that line of sight, Earth's curvature hides them from long-range sensors until they are nearly on top of their targets. Russian S-400 batteries are built to detect and kill high-flying aircraft or ballistic threats hundreds of kilometers out. Their engagement radars expect large radar cross-sections moving fast along predictable approaches. Low, slow, compact drones don't fit that profile. The returns blend into sea or ground clutter, and the narrow visual and radar signature makes them difficult to discriminate until the last moments before contact. Operators exploit this by programming flight paths that hug terrain or trace coastlines, using minor changes in altitude to keep the craft masked behind even small rises. Over water, wave action scatters the radar beam, further complicating tracking. Some units integrate basic terrain following routines, reading barometric pressure, or using laser altimeters to fly just meters above the surface. Multipath sensing, detecting radar energy bouncing off water, helps maintain course while staying hidden. When these drones do cross the radar horizon, the engagement window collapses. At around 150 kilometers per hour, a drone remains in a battery's effective kill zone for less than a minute before reaching weapon release or impact. That compresses the S-400's detect to engage chain to seconds, forcing operators to confirm the track, assign a firing unit, launch, and guide an interceptor against a target barely inside their range. A documented 17 drone raid on an S-400 site showed how this plays out. Approaching from multiple bearings at very low altitude, the swarm achieved simultaneous radar contact, leaving under 3 minutes before impact. Even with several kills, enough drones survived to damage radar vehicles and disrupt the battery's coverage.
Ukraine's domestically produced Beaver drones and other workshop-built models are tailored for this role. Several use composite fuselages to reduce radar reflections and low-noise engines that are harder to detect acoustically until very close. GPS navigation is backed by inertial systems, so even if signals are jammed en route, they can still press on to target coordinates.
For defenders, the effect is a resource trap. Long-range interceptors optimized for high-altitude aircraft are wasted on small, low RCS drones that barely appear in time to shoot. Each launch can cost hundreds of thousands or even millions, far exceeding the price of the incoming drone. Close-range guns can work, but only if they're already pointed in the right place at the right time. Hard to achieve against multiple simultaneous approach angles. The low horizon tactic flips the usual air defense logic. Instead of forcing attackers to climb or accelerate to survive, it forces defenders to fire expensive weapons in haste at fleeting, cheap threats, and still risk letting some through. Even modern integrated systems end up engaging swarms of small drones with munitions meant for fighters or cruise missiles. So if the big radars can be tricked by geometry and numbers, where do drone pilots aim next? At fuel and logistics. On a dimly lit stretch of rail deep behind the front, a sudden chain of fireballs erupts from a convoy of fuel tank cars, touched off by drones no larger than a backpack. There are no jets overhead, no artillery barrage. The opening move is the quiet hum of a small reconnaissance quadcopter orbiting unseen at altitude, feeding real-time thermal and visual imagery to operators stationed kilometers away. Every heat signature is mapped. Stationary tanker cars, storage tanks, and the slow sweep of security patrols. The job of this first platform is to watch, confirm, and fix the target so that when the strike comes, no second guessing is needed. This is the dual platform method Ukrainian teams have refined. One aircraft dedicated to surveillance and targeting, another designed purely for attack. The reconnaissance element, often a DJI Mavic in documented missions, can loiter for hours without noticeably increasing local alert levels. Once operators have precise coordinates and track data, they launch one-way FPV attack quadcopters in coordinated waves. Each craft is stripped of anything non-essential and carries a shaped charge warhead in the 2.6 to 3.2 kilogram range. That design is engineered to punch through 10 to 22 millimeter walls of tanker cars or storage tanks, igniting the vapor space inside in less than a second.
Hitting a hardened or moving fuel target takes more than a lucky approach. Rail convoys shift schedules and are often escorted, while static depots use earthen berms and barriers to contain fires. Russian electronic warfare adds further complexity, attempting to jam GPS guidance or disrupt control links entirely. To beat this, Ukraine's operators program triple-layer navigation into their drones. The primary layer is GPS, but it is paired with inertial measurement units that track movement by measuring acceleration and rotation, and an optical image matching system that compares real-time camera views with stored satellite or terrain images. If GPS is jammed, the platform switches automatically to inertial and optical guidance, pressing on toward the target even under intense interference. In the rail fuel train strike, this combination paid off. A Mavic orbited high enough to maintain line of sight, quietly sending thermal and visual updates. Guided by its feed, the FPVS approached from staggered directions at low altitude, each locked onto an assigned tanker section. Against the thin steel walls, the shaped charges focused their explosive force into a lance of superheated metal, punching clean through and igniting the volatile contents. Multiple tanks ignited almost simultaneously, and the chain reaction of secondary blasts and spreading fire overwhelmed any hope of saving the convoy. The line was blocked for days while damaged cars were cleared and track repairs made. Other missions used similar sequencing against fixed depots. Recon drones documented shifts in guard posts and the movement of fueling vehicles. FPVS then skimmed just over perimeter walls, steering into the most vulnerable tank surfaces. Simultaneous detonations multiplied the effect. In seconds, 2 or 3 primary fires became a dozen as flames leapt to adjacent tanks. The rapid escalation made firefighting impractical and forced operators to evacuate, ensuring the site was out of commission. Even small, low-cost craft can have this outsized effect when they are directed with precision. Instead of penetrating layered air defenses with crude aircraft and risking pilots, these strikes bypass most of the defended airspace entirely and destroy what keeps vehicles, ships, and aircraft moving. Each run forces the diversion of scarce resources to protect infrastructure that cannot easily be replaced. Patrols must expand, radars and guns must be repositioned, and fuel supply routes must be changed, slowing operations across a broad front. The strategic impact is clear. For a fraction of the cost of traditional airstrikes, these low-profile raids cripple fuel stocks, stall transport, and inject uncertainty into every logistic schedule. They turn the enemy's dependency on centralized fuel storage and rail movement into a vulnerability that a handful of determined operators can exploit. If a handful of cheap drones can cripple fuel supplies, how do you protect an entire logistics network under constant threat from the air? Ukraine's fusion of retrofitted MiG-29s with improvised electronics and coordinated unmanned swarms shows how asymmetric leverage can be built from mismatched parts. Together, precision-guided strikes from manned platforms and low-cost drones compress reaction times and overload defenses designed for conventional threats. The operational consequence is clear. Air defense doctrine and logistics protection must adapt rapidly or accept mounting losses in key assets and supply lines. These battlefield experiments are already forcing tactical changes and could redefine how air power is applied in future conflicts. Which countermeasures matter most? Better short-range air defenses, hardened logistics, or more aggressive seed? If you found this breakdown useful, like and subscribe, and comment which technology you believe will blunt these tactics: swarm mitigation, hardened fuel depots, or something else.